Hi everyone, we're going to pick up with 12.5 now, which is equations of lines and also equations of planes. And so we're going to do the first half of this section will be how to write the equation of lines, and then the second half will be the equations of planes. This is a little bit different than if you were writing the equation of a line from, say, algebra or even Cal 1 or Cal 2. The process is a little bit different in 3-space, but it's not terribly bad, I don't think. So let's try it out. A line in 3-space is determined by a point and on a line L and the direction of line L. So you need to know which way you're going and what point you're going through. And the direction is described by a vector. So we need a vector that is parallel to L. So we're going to let that be vector V. If a point P, X, Y, Z is some arbitrary point on your line L, and R naught or R sub 0 and R are both vectors that are position vectors for the points P naught and P. And if a vector A with representation connecting P and P naught together, then you have the triangle law for vectors so that your R equals your R naught plus your A. But since A and V are parallel vectors, then there's a scalar T that would give you A equals to V times some T. And so putting that into our triangle law gets you a formula, this little blue box right here, on how we're going to write the equation of a line based in vectors. And so that's a lot of words, but we're looking for this black line right here. We want the equation of this black line L. And then you'll notice there's a vector down here at the bottom, vector V. It is parallel to that line. So since it is parallel, going the same direction, we can use that to come up with L. And there are 2 points on our line L. One of them is right here and one of them is right here. And so since V is parallel to it, if we connect it together, we'll have a vector that is parallel as well. And so we can use the A with the V, since V and A are just parallel vectors. One's a multiple of the other, and so that's why we can multiply it by T. So hopefully that makes a little bit of sense what we're doing. But we have to find this R naught in this vector V, and then we can write the equation of a line. So this thing is called the vector equation of the line, where the T will trace out the line depending on what value of T you put in. So if you're going T is exactly equal to 0, you'll get this kind of pinkish, maroonish, reddish line in the middle. And then greater than T goes off to the right, less than T goes off to the left, and then that traces out our line. And so this is your vector equation, but we could also write the equation of the line in parametric or symmetric versions. So down here on number 2, we have the parametric versions of a line through the point that's parallel to a directional vector, A, B, C. So the A, the B, and the C are the coefficients in front of the T, where the X naught, Y naught, Z naught from your point gets added onto that. And then we have that equal to X, Y, or Z. So in general, if a vector ABC is used to describe the direction of a line, then the numbers A, B, and C are called directional numbers. And we use those directional numbers to write it not only as a vector equation or as a parametric equation, but we could also use them in what we're calling symmetric equations, where we eliminate the parameter t and we set all of the equations equal to each other. Now occasionally your A, B, or C, these A, B's, and C's could be 0. So it could be possible that this C, for instance, since it's coming from this vector up here at the top, that vector could have a 0 in it. And if it does, that's okay. We just don't set them all equal to 0, or set them all equal to each other. We would set what we can equal to each other, and then kind of write the other one off to the side saying, and by the way, this is true on this one too. And I'll show you what that kind of looks like. Okay, here are a few little true and false kind of things along the way. If you have two lines parallel to a third line, two lines that are parallel to a third line have to be parallel. Well, hopefully you can kind of imagine that has to be true. If you have two lines that are both parallel to this other line, then the first two lines have to be parallel as well. Two lines that are perpendicular to a third line are parallel. That would be false. And the best example of that is the axes themselves. Your x-axis, your y-axis, and your z-axis. So two lines that are perpendicular would be to a third. Both x is perpendicular to z and y is perpendicular to z, but that doesn't make x and y be parallel. Two planes either intersect or they are parallel. That is true. Just like in two space, two lines either intersect or they're parallel. It's the same idea. And then a plane and a line either intersect or are parallel. That's for the same reasoning. That would also be true. Okay, this one says find the vector equation and the parametric equations for the line through the point 0, 14, negative 10 that is parallel to this line given in a parametric equation format. X equals negative 1 plus 2t, y equals 6 minus 3t, and z equals 3 plus 9t. And so we need our vector v. Remember, if it's in parametric, your vector is sitting in front of your t's. So our vector is 2, negative 3, 9. That would be my vector v. I also need a vector r naught. Well, let's actually do a different color, just so that I can show you where all these things are kind of going together at. So we need a vector r naught as well. R naught is going to be based on our point up here. So that's what we're going to base R naught on. R naught will be the vector 0, 14, negative 10. By the way, you could also do this in IJK notation if you'd rather do IJs and Ks instead of this notation. And so now our vector equation, our R, so to speak, remember that's the formula R naught, or actually, let's again keep all the colors the same, just to make it pretty, I guess. So we'll have R naught plus T times V. So that's going to be our formula to come up with the equation of the line. And so we just write these things in here. We'll have this is equal to R naught, which is my 0, 14, negative 10, plus T times my vector V, 2, negative 3, 9. And what we'd like to do is kind of stick some of this stuff together if we possibly could. Make it look a little bit nicer, for instance. You could leave it like this. This is not a wrong notation to put it in. But what we usually like to do is try to get it to just one vector. So you'll notice if I multiply the t across, I'll end up with 2t for the first term. It's actually 2t plus 0. The second term, I'll have negative 3t, and then I'll have plus 14. And then I'll have 9, oops, sorry, if I'm doing all the same colors, I guess I should stick with the same colors. I'll have a 9t, and then the minus 10. So that would be my vector equation. Or, like I said, you could put it in IJK notation. This would be 2ti plus negative 3t plus 14j plus 9t minus 10. Oh, I almost ran out of room. K. There's a K on the end right there. So you could write it that way as well if you'd rather do the IJK notation. So I'm partial to the not IJK notation, so I would write it like this. But you could write it either way. And then it says also to find the parametric equations of that line through that same point. That's fairly easy to do. Your parametric equations, if you write the vector equation the way that I have boxed in here, then that is the parametric equations just in a vector. And so my parametric equations would just be x equals the first one, y equals the second one, and z equals the third one. And that is your parametric equations. Another reason I like doing it that way. You could also get those from the IJK notation. Just whatever is multiplied by I is x, whatever multiplied by j is y, whatever is multiplied by the k is the z term. Okay, let's do another one. Find a vector equation and parametric equation for the line going through the point 1, 0, 6, and it's perpendicular to the plane x plus 3y plus z equals 5. So you still got to find the same two things. You need a vector v, and you need that r0 vector. So my vector v, in this case, since this is my equation of my plane, and it's perpendicular to that, my normal vector is going to, or my orthogonal vector, my cross product basically, is going to come from these values right here. And so I take those from the 1, the 3, and the 1. So those three numbers from the plane are my vector v. Since it's perpendicular, we'll have a vector from those coefficients. And then I also need the r0. Just like on the last one, the r0 comes from the point, whatever the point is. So my r0 will come from the 1, the 0, and the 6. So my vector r will be r0, which is 1, 0, 6. Oh, sorry, that bracket I guess technically should have been in the blue color as well. Plus t times my vector v, which is the 1, the 3, and the 1. And so just like before, what I want to do is kind of combine this together and make this 1t plus the 1 from the r0. Sorry, I left the naught off of there. Then I'll have 3t, but I have a 0 in the r0, so I don't add anything to it. And then the 1t, and then I'll have a plus 6. So you could write it like this. That's your vector equation. You could also, like I said, you could write it in the IJK notation. That would be t plus 1i, 3tj, and t plus 6k. So if you want to write it in the IJK notation, you could do that as well. Parametrically, we're just going to pull them straight off of whatever is in front of the IJK or whatever is in front of my different pieces of my components of my vector. And I'll say that x equals t plus 1, y equals 3t, z equals t plus 6. Oops, I went right to the 6, didn't I? See if I can't fix that a little bit. And we'll, whoop, how about that? So that would be my parametric equations. If you want to do symmetric, by the way, you just take your parametric ones, solve them all for t, and set them equal to each other. I'll show you that on the next one. So this one says find parametric equations and symmetric equations for the line through the points, and it gives you the 2 points, the 0, 1/2, 1, and the 2, 1, and -3. So now we have 2 points. We don't have a vector v that we can pull off of a plane or another line. And so here, my vector v, I'm just going to find the vector by subtracting the points. I'm going to do 2 minus 0, 1 minus 1/2, -3 minus 1. So I'll end up with the vector 2, 1/2, and -4. Now you might wonder, what if you did it the other way around? What if you did the first point minus the second point? You'd end up with a vector just going the other direction. That's all it would be. This vector v has to be parallel to the line that we're looking for. So we need that, and we need either the, if you're not going to find the vector equation, you don't need the R naught. You could just skip doing the R naught and pick one of the points. So since they go through both points, it actually doesn't matter which point you pick. I'm going to pick the second one. Now this is very, 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 very important. If I pick the second one and you were to pick the first one, that doesn't mean that I'm right and you're wrong, or you're right and I'm wrong. You'll get 2 different sets of an x, y, z for the parametric equations. They will look different, and they're both correct. So you could easily pick the first point and come out with something, that would be an equivalent answer, but they won't look the same. But the 2, 1, and the -3, those are my points that I would have on my parametric equations. So my parametric equations would be x equals, I would have the 2 from the point, and then I would have the 2 from the vector. Y, I would have the 1 from the point and the 1/2 from the vector. And z, I would have the -3 from the point and the -4 from the vector. These are my parametric equations. These are the parametric equations for my line. To find the symmetric ones, I have to take each one of those and solve it for t. So if I take that first one and solve it for t, that would be x minus 2 equals 2t, or dividing by 2, I'd have x minus 2 over 2 equals t. On the y one, I would have y minus 1 equals half of a t, or y minus 1 over 1/2 equals t. Or you could say 2 times that if you want to. I'm leaving it like that for a reason, though. And then your z would get added 3 to the other side and divide by -4. So I have z plus 3 over -4. Since they're all equal to t, then I set them all equal to each other. X minus 2 over 2 would be equal to y minus 1 over 1/2, which would be equal to z plus 3 over -4. These are my symmetric equations for the same line. Notice the way that I have it written here, the numbers across the bottom are from the vector v. The numbers that are subtracted on top are from the point that I used. So if you used the other point, you would have different numbers on the top. So hopefully that makes sense. Okay, this one says find the parametric equations and symmetric equations for the line through the point 2, 1, 0 and perpendicular to both I plus j and j plus k. So here we're not given a vector v, but we know that it has to be perpendicular to these 2 vectors. And we remember from the last section that my vectors that are perpendicular to two other vectors can be easily found by doing the cross product. So here you have a little bit more work to do. Our vector v that we're going to be using will actually be I plus j crossed with j plus k. So if I do my cross product for those vectors, I'll have a I, j, k across the top. I plus j would be 1, 1, 0, and j plus k would be 0, 1, 1. And so I'd have the 1, 0, 1, 1 on the I minus 1, 0, 0, 1. Ooh, an identity matrix for those of you in linear algebra. And the k would be 1, 1, 0, 1, k. So I'd get 1 times 1 is 1 minus 1 times 0 is 0. I'd get 1 times 1 is 1 minus 0 times 0 is 0. And 1 times 1 is 1 minus 0 times 1 is 0. So my vector would be the vector I minus j plus k. Or if you want to write it as 1, negative 1, 1. It would be the same thing. So if I want to find my parametric equations first, I need a point, which I have. There's my point. I have a vector v. And so my parametric equations would be x, y, and z. You would list the point first. 2, 1, 0. Then I'd have plus 1t. So there's a 1 from the vector times t. Then there's a negative 1 times t. And I'm writing the 1s on there just to make sure you see where the 1s come from. And then I have 0 plus the 1 t. So my equations would just be 2 plus t, 1 minus t, and t, which is kind of nice, I guess. These are my parametric equations. It also asks me to find the symmetric ones, so I have to take those and solve it for t, which is not too hard here since it's just a t on most of them. But I'll have an x minus 2 to give me t. I'll have a y minus 1 equals negative t, so I'd have to divide by negative 1 on that one. And if z equals t, well then z equals t. You already solved for it. So, and so I set them equal to each other, so I'll have x minus 2 equals y minus 1 over negative 1, which equals z. And that would be my symmetric. You could divide the negative 1 in there if you want to make it look a little bit better. But anyway, these are my symmetric equations. Again, if you notice, the numbers that they're divided by are the numbers from the vector. The x minus 2 would be divided by 1. The z would be divided by 1. And the point, the 2, 1, 0, is what gets subtracted off. You have an x minus 2, a y minus 1 on top. The z has a minus 0 on it that's not shown, but that's what you're doing. Okay, let's try this one. Find the parametric and symmetric equations of a line through the point negative 6, 2, 3. Now we are parallel to the line 1/2 x, which equals 1/3 y, which is z plus 1. These are your symmetric equations of a line. So you're given a symmetric equations and a point here. So if you notice the symmetric version here, you'll notice that there's nothing subtracted from the x and there's nothing subtracted from the y. Technically, this would be x minus 0 over 2. and this would be y minus 0 over 3, and this would be z plus 1 over 1. So the 2, the 3, and the 1 that's on the denominator would be your vector v in this case. Since it's parallel, we'll have the same vector. So vector v will be the 2, the 3, and the 1 that's on the denominator of my line that was given to me. So I have that, and I have a point, so I can write the equation now. I'm going to use this point here. We're doing parametric first, so I would do x, y, and z. You write the point down first, -6, 2, 3. I don't know if y'all like the vertical way I do this, but comes in kind of handy if you notice that you take that point, turn it vertically, and write it straight down. Then you take the vector v, write it straight down, 2, 3, and a 1. That gets multiplied by t. And that is your parametric equations. Then if I solve those for t, I could write them symmetrically like the original equations were given to me. So the first one, I would have an x plus a 6 divided by 2. The next one, if you move the 2 over and divide by 3, you would end up with that. And you subtract the 3, and you would divide by 1, but there's not really a 1 there to divide by. And so I would have x plus 6 over 2 equals y minus 2 over 3, which equals z minus 3. These are your symmetric. And notice, oh, 2 m's, symmetric. Notice that it has the same format as the line that I started with. It's an x plus a number over 2. It's a y plus minus a number over 3. Z with a number. It's the same format the other one was because you have the same vector on the bottom, the 2, the 3, and the 1. Okay, how about this one? Is the line that goes through the point -4, 6, 1 and -2, 0, 3, is that line parallel to the line that would have gone through the points 10, 18, 4 and 5, 3, 14? Well, you have to come up with two vectors. Kind of like on the last one, you'll notice that the vector v was the same since it was parallel. We have the same vector v on the bottom. Here, if we have the same vector v, or if we have a constant multiple of vectors, then we could say basically they are parallel. So we need to find two vectors. So I'm going to find two vectors based on the first 2 points. So this point and this point. I'm going to call that v1. So we're going to have two different vector v's here. So I'm going to call one v1 and one v2. v1 I'm going to say is -2 minus -4, 0 minus -6, and -3 minus 1. That would be -2 plus 4, which is 2. 0 minus -6 would be +6, and a -4. And then I'm going to come up with a different vector using these other 2 points. So v2 will be 5 minus 10, 3 minus 18, and 14 minus 4. So I'll have -5, -15, and 10 for my other vector. Now, to see if they're parallel, you have two options. Can you come up with that one is a multiple of the other? Or you could do the cross product and use that definition. I like the fact of trying to see if they are multiples of each other. For instance, the first one, there's a 2 in common. If you were to factor the 2 out, this would be 1, 3, and -2. The other one, there's a -5 in common. If you pull out a -5, you would have a 1, a 3, and a -2. So you have the same base of 1, 3, -2 on both of them. because of that, they are constant multiples of each other. For instance, you could say that the second one is gotten by the first one by multiplying it by -5 halves. So I could say that V2 is V1, but I had to get rid of the 2, so I divided by the 2, and I had to multiply by -5. So they are constant multiples of each other. And since they are constant multiples of each other, they are parallel. And that's the quicker way to do it. You could, but like I said, you could also do the cross product definition if you want to. Okay, instead of writing the entire equation of a line, we could just do a segment of that line. And so a line segment from R0 to R1 would be given by the equation 1 minus t gets multiplied by R0 instead of just having R0, and then t times R1. So you'll have two different vectors, R0 and R1, and then one of them has a 1 minus t on it. We don't do a whole lot with line segments, but I will show you this one how it works. Since R0 and R1 are actually vectors that are going towards a point, then we could use the 2 points to come up with R0 and R1. So I'm going to let one point be R0 and one point be R1. And you say, well, does it matter which one's which? Officially, no. But if you do it backwards of the way that I'll do it, your line might look different. So I'm going to let R0 be just the first one that's listed. So I'll have the vectors 6, -1, and 9. And I'll do the vector R, R1 by the way, would be 7, 6, 0. And remember, you can do this in IJK notation if you'd rather do that. And so my equation of my line segment would be 1 minus t times the vector R0, the 6, -1, 9, plus t times the vector R1, 7, 6, 0. And then we just kind of manipulate this and make it look a little bit nicer. So I'll have a 1 times that whole vector. That'll give me the 6, -1, 9 again. Then I'll end up with a minus t on each one of them. So that'll be a 6t, a -t, and a 9t. I just left the negative in front. And then I'll have a 7t. Oops, left the t off. 7t, 6t, and still 0. And so what I want to do is gather what I can together. I have a 7t, a minus 6t because of the minus in front of the brackets there. That gives me a t and a 6, so I get t plus 6 if you combine the first three terms all together. I have a 6t and a minus -t, so that'll give me a 7t with the -1 in front. And then I got 0 on the last one, but I have a minus 9t plus 9 on that last part. And that's for t's being between 0 and 1. So you could write it like that, or like I said, you could put an IJK notation. It just all depends on how you want to write it. So hopefully that makes some sense. Okay, let's determine whether the line L1 and L2 are skew, parallel, or intersecting. So skew means they don't intersect, but they're not parallel either. So you have a line going one direction and one going a totally different direction. But in 3 space, they don't necessarily intersect when they do that. And if they intersect, we'll find the point of intersection. So I have 2 lines given parametrically. And so what I could do is I could say, let's look at the direction vectors. And so my direction vector here for V would be the 2, the -1, and the 3, the coefficients that are in front of the t's. And my other vector, I'm going to call that V1 since I'm going to have actually 2 vectors here. My other vector, let's make it a different color as well. My other vector, I'll call it V2, from the other equation, I have a 4, a -2, and a 5. 4, -2, and 5. So if they're parallel, one would have to be a constant multiple of the other. Which, that's not going to work here because notice there's nothing in common on the first one and nothing in common on the second one, so you can't factor anything out. So you'd have to go with, could you just multiply something from the first one to the second one? If I multiply the first one by 2, I will get 4 on the second one. But if I multiply 2 times -1, I don't get -2, and I definitely don't get 2 times 3 is 5. So these are not parallel. Parallel. How do you spell parallel? Oh, it's up there above that. I guess I could have looked up there. Oh, that's awful. I didn't hit eraser. So let me try that again. I'm going to try to spell parallel correctly. Parallel. They're not parallel because they're not multiples of each other. So in this case, you can not worry about the parallel part. So they either have to be skew or intersecting, one of the two. And so how do we check that? Well, let's see if they intersect. If they intersect, then the x's have to be the same. I mean, you can set them equal to each other. And the y's have to be hit the same spot on the t's, and the z's would have to be hitting the same spot. So let's see what happens. I could take 3 plus 2t and set that equal to 1 plus 4s. And then I could set 4 minus t equal to 3 minus 2s. Or I could set 1 plus 3t equal to 4 plus 5s. So I'm setting the x's, the first components together, the second components, the y's, and the z's, set them all equal to each other. And so then we got to see, can we solve for the s and the t? If we get something that doesn't make any sense, then we don't have an intersection point, and they're skewed. If we do get something, then that'll be the intersecting point. And so that's kind of our plan here. So we have 3 equations. We only have 2 unknowns. So we can do this by elimination, would be one option, or you could do a matrix and row reduce it. Lots of different things you could do here. What I'm going to do is I'm going to take this second one here, and I'm going to double it and write it underneath here. So 4 times 2 is 8 minus 2t equals, doubling it gives me 6 minus 4s. If I add those together, I get 11, those cancel, I get 7, and those cancel. Well, 11 doesn't equal 7. That's not good. You say, well, maybe that's just an error. It's not going to be. It's going to end up that we're going to be skewed because they won't find the spot that they intersect. But maybe you want to try a different one just to make sure that what's going on here is not bad. We could try a different one. What if we tried, what's another one that could be easily tried? Well, let's go the other way with this one on this one. And I multiply it times 3 instead. I'll get 12 minus 3t equals 9 minus 6s. Here I'll get 13 equals 9, 10, 11, 12, 13 minus s. And you go, oh, well, see there, I got an s value. So if I subtract the 13 off, I get 0 equals negative s. So s had to be 0. And you might say, okay, well, that's fine, right? So if s is 0, then if I plug it in on one of the other ones to find t, you might say, okay, well, let's just plug that little sucker back up in here. Say 1 plus 3t equals 4. Subtract that off, and you can say, oh, well, t must have been 1. Okay, so if s is 0 and t is 1, that works for the z part. Would that work for all of them, though? If I was to plug 1 back into, say, the very first one with the x's, if I was to plug in 1 for t and 4 and s for 0, would that work? Well, I get, back over here, 3 plus 2 times 1. Would that equal 1 plus 4 times 0? Well, you get 5 equals 1. So, no. It has to work for all three for it to work at all. And so since it doesn't work, the 11 equals 7 kind of really gave it away from the get-go. But if you didn't notice that and you maybe did one of the other ones and you got two values, you do have to plug those back in to make sure it works for all of them. And if it doesn't work for one, then they don't intersect. This is a skew set of lines. They do not intersect. Okay, let's talk about planes now a little bit. So a plane in space is determined by a point in the plane and a vector in, and that's called a normal vector. When you talk about tangent lines in Cal 1, occasionally you'll talk about a tangent line and you'll talk about a normal line. A normal line is the line that's perpendicular. So that's what we're talking about here. A normal vector is orthogonal or perpendicular to the plane. So if we have our point P x, y, z that's in my plane, and we have an r naught and an rb position vectors, you kind of notice this along in the picture down below as well. Then the vector r minus r naught is represented by the points connecting P to P naught. And the normal vector is the one coming out of the plane. That would be the reddish line in the picture below. That's orthogonal to every other vector in that plane. And since it's orthogonal to every single vector in the plane, then it has to be orthogonal to the one vector that we're worried about, which is r minus r naught. And so we could have that the normal vector dotted with that subtracted r minus r naught would have to be 0. Or we do a little manipulation and we'd say that r naught dotted with n and n dotted with r, they actually have to be the same thing. And these are the vector equations of the plane. So to obtain the scalar equation of a plane, we could take the n vector, the r vector, and the r naught vector, multiply them, do all the dot products, adding, subtracting, and all that sort of stuff. And we end up with this box 7 that says the scalar equation of the plane is a times x minus the x value, b from the normal vector times y minus the y value, and c from the normal vector times z minus z naught equals 0. And then you can make it look a little nicer if you made it ax plus by plus cz plus a constant equals 0 if you wanted to. Usually I wouldn't go that far. I would stop with it like it looks in box 7. So we're going to find the equation of a plane. So it'll make a lot more sense actually when we actually do one. So find the equation of the plane through the point 5, 3, 5 with a normal vector 2I plus j minus k. So since they give you the normal vector, that is great. You don't know how great that is. So your normal vector is 2, 1, negative 1. Or you can leave it 2I j minus k if you want to. Doesn't matter. And we have the point 5, 3, 5. So I'm going to jump straight in and I'm going to write this as my scalar equation. That's the one that I think looks the best. And so we'll have the 2 from the normal vector times x minus the x value plus there'll be a 1 right here if you want to put the 1 in there, times x minus the x value, which is 3. Oh, sorry, I said x. I meant to say y. By the way, that's going to happen a lot because I get used to writing the letter x. And then I'll have a minus 1 times z minus z value, which is 5, equals 0. So that's where all the numbers would go. This is 2 times x minus 5 plus y minus 3 minus z minus 5 equals 0. Oops. That is your scalar equation of your plane. You could, like I said, you could rearrange it and get the x, y, z by itself if you wanted to. If you wanted to keep going further, this is 2x minus 10 plus y minus 3 minus z plus 5 equals 0. Move all the constants to the other side, and you could say it's 2x plus y minus z equals, the 10 and the 3 make negative 13, plus 5 would be negative 8. So if you move it to the other side, you could make it, say, positive 8. So either one is actually good. I don't see the point in doing that much work if it takes it when you have a scalar equation like the first box. That's where I would stop. So that's as easy of an equation of a plane that you can ever get. Okay, find the equation of a plane through the point 1, negative 1, negative 1, and is parallel to this equation of the plane, 5, negative 1, 5x, negative y, and minus z equals 6. Since they're parallel, this little fact that says that it is parallel to this plane, if it's parallel, they have to have the same normal vector. And so the 5, the negative 1, and the negative 1 in front of the x, y, and the z would be my vector v that I would use. Or, sorry, we're on the ends now. So this is actually my normal vector. So I'll call it n instead. So my normal vector n would be the same for both planes. And so now I have a point and I have a normal vector, so I just start writing the answer down. It is 5 times x minus the 1 from the point minus 1 times y minus negative 1 minus 1 times z minus negative 1 equals 0. So I'll make this say 5 times x minus 1 minus y plus 1 minus z plus 1 equals 0. And that is my scalar equation of my plane. And again, if you wanted to go, another couple steps and say this is 5x minus 5 minus y minus 1 minus z minus 1 equals 0, I get 5 and 1 will make 7, negative 7. So if you move it to the other side, you'd have a positive 7. So you could write this in this form if you'd rather make it look a little bit different. But both forms are correct. Okay, this one's going to be probably one of the worst ones to do. Find the equation of a plane through the points 0, 1, 1, 1, 0, 1, and 1, 1, 0. Here you have no vectors to work with, no equations of planes to work with. So you have to come up with the normal vector yourself. And so I'm going to call these different things. I'm going to call this point P, this point Q, and this point R. So just going down the list. So I need to come up with vectors that are connecting these two things. So like for instance, I'm going to do PQ. that vector would be subtract the q minus the p. The q minus the p. Q minus the p. Subtracting the q minus the p. So I'll get 1 minus 0, 0 minus 1, and 1 minus 1. So I'll get the vector 1, negative 1, 0. So that would be one vector. Then maybe I'll do PR. And you say, well, does it matter? Again, it does not. So if you do different points in a different order, you'll get a different looking answer. But if I do PR, I'll do 1 minus 0, 1 minus 1, and 0 minus 1. So that would be 1, 0, negative 1. So I did the R points minus the P points. That's two vectors. Those two vectors are in the plane because the points are in the plane. I need a vector that is normal to the plane. So I need to do a cross product to come up with an orthogonal vector. So my N would be the cross product of PQ crossed with PR. Oops. Oh yeah, that's right. R. And so I would have an I, a J, and a K. I have 1, negative 1, 0, 1, 0, negative 1. So your I would be using the determinant of the negative 1, 0, 0, negative 1. Your J would be using 1, negative 1, 1. Oh, sorry, not negative 1. Read the wrong line there for a moment. J uses 1, 0, 1, negative 1. And K would use 1, negative 1, 1, 0. So I have negative 1 times negative 1, which is 1, minus 0 times 0 is 0. I have 1 times negative 1 is negative 1, then minus 0. And I have 1 times 0, which is 0, minus 1 times negative 1, which is negative 1. So this gives me I, J, and K, or the vector 1, 1, 1. I laugh because it's kind of ironic that it came out to be 1, 1, 1. Okay, now I have a normal vector. And I need a normal vector and a point in the plane. That's all I need. I actually have 3 points in the plane. So which one do you pick? Truthfully, whichever one you want to. I'm going to pick the first one. And I'm going to get the 1 from the vector times x minus 0 from the point plus the 1 from the vector times y minus the 1 from the point plus 1 from the vector times z minus 1 from the point equals 0. So this is x plus y minus 1 plus z minus 1 equals 0. That is the equation of the plane. Or again, this one's really easy since there's not really anything multiplying times those parentheses. The 1 and the 1 make 2, so you could write it as x plus y plus z equals 2. If you want to write it like that, it would be the same sort of thing. But that one's probably one of the ones that takes the most amount of work because you do have to do a cross product. So I'll show you another one kind of like that does sort of the same thing. So this one says find the equation of the plane that passes through the point 3, 5, negative 1. But in this case, it contains a line. There's a line that goes straight through this plane given by 4 minus t, 2t minus 1, and z equals negative 3t. Now, here this line is made up by a vector, but that vector is in the plane. I need a vector that is orthogonal. to the plane. So I need to come up with two non-parallel vectors in the plane so that their cross product will be perpendicular, would be the normal vector. Well, one vector I could use is the vector that's from the line, the -1, the 2, and the -3. I could use vector v as -1, 2, and -3 from my equation of a line. That is a vector that is in the plane. And so then I need a different vector in the plane as well. The point, this point at the top, this 3, 5, -1, that is not on this line. So this point up here is not on this line. I know that because what value of t would give you that point? Well, say for instance on the z coordinate. If I let t be 1/3, 1/3 times -3 gives me -1. So the t would have to be the same for all of them. So go to the x. 4 minus 1/3, that's not 3. So I know that point is not on that line. So what I could do is come up with another vector from that line. And so, for instance, how about we do this? What if I let t be 0? If t were 0, then I would get 4, -1, 0 as a point. I'm sorry, that should not be a vector. It should be a point. I'll get the point, not the vector, the point for -1, 0. So now I have 2 points, the 3, 5, -1, and the 4, -1, 0. Those are both points in the plane. I could find the vector that connects those points. So I'll call it, say, vector u. And I just have to subtract those values. 4 minus 3. So this would be, actually, I might want to scoot this over if I'm going to try to write this all on one line. I'll put it over here. And so I would do the 4 that from the point I just found minus the 3 that's from the point that was given to me. And hopefully that makes sense. And then I'll do the -1 minus the 5. And then I'll do the 0 minus the -1. So that'll give me the vector 1, -6, 1. Now I have two vectors, v and u, that are in the plane. So the cross product between those two vectors would be my normal vector. And so my normal vector n would actually be my vector v crossed with my vector u. Crazy, isn't it? I always thought it was. So I have an I, a j, and a k. And I'm going to cross the -1 to -3. I'm going to cross that with the 1, -6, and 1. And whatever that comes out to be will be my normal vector. So let's see what it comes out to be. The I is going to use the 2, the -3, the -6, and the 1. The j is going to use the -1, the -3, the 1, and the 1. And the k is going to use the -1, the 2, the 1, and the -6. So this is going to give me 2 minus negative 6 times negative 3 is 18. Negative 1 times 1 is negative 1. Minus 1 times negative 3 is negative 3. Okay. And negative 1 times negative 6 is 6. And 2 times 1 is 2. So I'm left with negative, let's see, yeah, negative, yeah, negative 16 I. The negative 3 makes 3, minus 1 is 2, so I'll end up with a minus 2j and a 4k. Or, if you want to write it in the other notation, negative 16, negative 2, and 4. That's my normal vector. Now I have a normal vector and a point. So you write down your answer. Your answer would be the negative 16 from the normal vector times x minus the x value of the point. Then I'll have a negative 2 from the normal vector and a y minus the 5 from the point. Then I'll have a 4 from the normal vector times z minus, or actually plus if you want to switch the sign already, but it's a negative 1, equals 0. So I'm going to have negative 16 times x minus 3 minus 2 times y minus 5 plus 4 times z plus 1 equals 0. And that would be my scalar equation of my plane through that point with that particular line in it. And again, if you wanted to, you could rearrange it and set it equal to a number. I won't worry about doing that here. You could also, if you notice, the entire thing is a multiple of 2. You could divide everything by 2 if you want to simplify it a little bit. I'm not going to worry about that because the negative 16, the 2, negative 2, and the 4 actually is my normal vector, so I'm going to leave it like that. Okay, this one says, use intercepts to help sketch what this plane would look like. This might look awful, but I'm going to try to actually draw this one out. The intercepts are not too bad. So you might remember from algebra that your intercepts is what you get when you let the other letter be 0. So if you want to find what the x-intercept is, you let y and z be 0. And so if y and z are both 0, all you're going to get is 2x equals 10. So x had to be 5. So you just use the 2x and the 10. So I get the point 5, 0, 0. If you want the y-intercept, you let x and z be 0. So you're only going to get, the y and the 10. So we'll get 5y equals 10. So y was 2. So I'll get the point 0, 2, 0. And if you want the z-intercept, you let the x and the y be 0. So all you'll get is z equals 10, which literally is z equals 10. So you get 0, 0, 10. So I get those 3 intercepts, and then I plot those 3 intercepts and see what happens. So I'll have an x-axis, a y-axis, and your z-axis. So I got to go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is my z-intercept right there. On the y-axis, I go up to 2. 1, 2. That looks kind of boring. I'll just put some more tick marks on there just to make it look, kind of symmetric. So y equals 2 would be right here. And x was 5. So 1, 2, 3, 4, 5. About right there. And so the plane connecting those would be going through this point here, over to this point, and down this one. And so that would be what the plane looks like, which I might, point out that's probably the best looking thing I've ever drawn in my life. So hopefully you can kind of tell that's what my plane would look like. And it's kind of just slicing through all 3 axes. Okay, find the point at which the line intersects the plane. So if you're looking for, this is a line here. So these first 3, the x, the y, and the z, this is your line intersecting the plane, x plus 2y plus minus z equals 7. This looks kind of complicated, but it is one of the easiest things you can do. If you know x equals 2 minus 2t and y equals 3t and z equals 1 plus t, you just take this and plug it in where the x's, the y, and the z's are. And that's all you're doing. So that x becomes 2 minus 2t. Then I have 2y, y was 3t. And then I have a minus z, but z was 1 plus t equals 7. So you're just plugging in the x, the y, and the z. So I get 2 minus 2t plus 6t minus 1 minus t equals 7. So gather all my t's together. I have 6 minus 2 is 4, minus 1 is 3. So I have a 3t. And I have a 2 minus 1, which is just 1, plus 1 equals 7. So that means 3t was 6. So t was 2. And so if t is 2, then I just have to plug that back in, plug this t value back into the line. And so x would be 2 minus 2 times 2, which would be 2 minus 4, which is negative 2. My y would be 3 times 2, which is 6. And my z is 1 plus t, which is 2, which is 3. So the point where the line intersects the plane is negative 2, 6, 3. That is the point where they come together at. So hopefully that wasn't too bad. That's probably one of the easier ones you'll see. Okay, if you have these 2 planes are parallel, if their normal vectors are parallel, and we have kind of already talked about that a little bit. And so if the planes are not parallel, they intersect at a single straight line, and the angle between them is this formula. It's actually the same formula that we talked about how to find the angle between 2 vectors. You do the dot product divided by the magnitude of each one. So it's the same formula we talked about back in 12.3. So this example down here says determine if the planes are parallel, perpendicular, or neither, and find the angles between them if they are neither. Well, you're going to base this off the normal vectors. If you have a line, if you have a plane, the normal vectors are the coefficients in front of the x, the y, and the z. So my normal vector for the first one would be, oops, sorry, got the little bracket here. For the first one would be 1, negative 1, 3. And the normal vector for the other one is 3, 1, negative 1. So those are going to be my 2 vectors. The easiest thing to check, are they parallel? Is one a multiple of the other? And they are not. These are not parallel because they're not multiples of each other. And you can kind of see that pretty quickly. To go from the first one to the second one, you can multiply by 3 on the x coordinate or the first coordinate. 1 times 3 would be 3, but if you multiplied the last one by 3, you wouldn't get -1. So they're not multiples. So then we're going to go with the formula. We're going to do the dot product between them and then divide by the magnitude. So cosine of theta would be the dot product, so I would do 1 times 3, doing the first ones. The second components, -1 and 1. And the third components, 3, -1. Divide that whole thing by the magnitude of each one. So that's a 1 squared, -1 squared, and a 3 squared for the first vector. For the second vector, I'll have a 3 squared plus 1 squared plus -1 squared, which is actually the same thing from the first vector. So on top, you'll get 4 minus 1 minus 3. And underneath, you'll get 3 squared is 9, 10, 11. But it really doesn't matter what's underneath because 4 minus 1 is 3 minus 3 is 0. If your dot product ever comes out to be 0, then you have to be orthogonal. You know what? I have no idea why in the world I said that 3 times 1 is 3. I just noticed that. Oh, sorry, 3 times 1 is 4. I added them. Oops. So anyway, that's a good point though. If they do come out to be 0, they have to be orthogonal. This one, sadly, does not come out to be 0 because I cannot multiply. This comes out to be -1. Oops, that's really a lot bigger for some reason. This one comes out to be -1 on top, not 0. And so since it comes out to be not equal to 0, that means it is not perpendicular. So this -1 not being 0 means it's not perpendicular. And so we can find the angle between them because theta would just be cosine inverse of -1 over 11. And we go to the calculator. It's going to be close to perpendicular. Type that in the calculator. I think it comes out to be 95.2 degrees. And so that would be the angle between the two planes. So I'm going to try another one of those, and maybe I won't mess this up with my bad multiplying. So determine if the planes are parallel, perpendicular, or neither, and see what happens. So my first normal vector would be 1, 2, -1. My other normal vector, oops, that should be a 2 there, would be 2, -2, and 1. Those are the values in front of my x, y, and z. Again, they're not parallel for the same reason the other one wasn't. They're not multiples. If you take the first component on n1 and double it, you get the first component on n2. So if you double each one of them, 2 times 2 will make 4, not -2. So they're not parallel because they're not multiples. So the other option is, can we do the angle between them and the dot product? So let's try that. So cosine theta would be 1 times 2 plus 2 times -2 plus -1 times 1. That's your dot product. On the bottom, we'll have 1 squared plus 2 squared plus -1 squared. And on the second one, we'll have 2 squared plus -2 squared plus 1 squared. So my dot product will give me a 2 minus 4 minus 1, which will not be 0. So we're not going to be perpendicular either. On the bottom, we'll have 2 squared is 4, 5, 6. And 2 squared is 4, and 4 is 8, plus 1 is 9. So 2 minus 4 is -2, minus 1 is -3 over 3 root 6, or -1 over the square root of 6. So since this dot product didn't come out to be 0, it is not perpendicular, which means we can find the angle between them just by doing cosine inverse of that thing in the calculator. So if you type that into the calculator, hopefully you get somewhere close to 114.1 degrees. And that is how you do equations of lines and planes and angles between the planes as well. So hopefully that's not too bad. And that is the end of this particular section. So next section will be 12.6.